History of matrix. Matrices are an essential mathematical tool that is used to represent linear equations, transformations, and other related concepts. The history of matrices can be traced back to ancient Egypt, where they used matrices to solve linear equations, though they didn't call them matrices at the time. In the 19th century, matrices began to take shape in their modern form, thanks to the significant contributions of mathematicians such as Arthur Cayley and James Joseph Sylvester. Arthur Cayley was a British mathematician who made significant contributions to the development of algebraic geometry, number theory, and matrix algebra. He introduced the concept of the matrix in 1858 and developed a method for determining the inverse of a matrix. Cayley's work laid the foundation for the study of matrices and their applications in various fields. James Joseph Sylvester, also a British mathematician, is credited with coining the term matrix in 1850. He made important contributions to the study of matrices, including developing methods for finding determinants and inverses. Sylvester's work helped to establish matrices as a fundamental concept in mathematics. Over the years, matrices have been used in various fields, including physics, computer science, and engineering. In physics, matrices are used to describe the behavior of particles and waves, while in computer science, they are used in graphics processing and artificial intelligence. In engineering, matrices are used to analyze structures, such as buildings and bridges. In conclusion, the history of matrices is a rich one, spanning several centuries and involving the contributions of many brilliant mathematicians. Today, matrices continue to play a crucial role in mathematics and various fields, making them a vital tool for anyone studying science and technology. Types of matrix. 1. Square matrix. A matrix where the number of rows is equal to the number of columns. 1. For example, a 3 by 3 matrix or a 4 by 4 matrix. 1. Square matrices are used to represent linear transformations and to solve systems of linear equations. 2. Identity matrix. A square matrix with ones on the diagonal and zeros everywhere else. 2. For example, a 3 by 3 identity matrix would be 1, 0, 0, 0, 1, 0, 0, 0, 1. 2. Identity matrices are used in linear algebra to represent the identity transformation. 3. Diagonal matrix. A square matrix where all the off-diagonal elements are 0. 3. For example, a 3 by 3 diagonal matrix would be 2, 0, 0, 0, minus 1, 0, 0, 0, 5. 3. Diagonal matrices are used to represent transformations that scale each coordinate independently. 4. Upper triangular matrix. A square matrix where all the elements below the diagonal are 0. 4. For example, a 3 by 3 upper triangular matrix would be 1, 2, 3, 0, 4, 5, 0, 0, 6. 4. Upper triangular matrices are used in linear algebra to solve systems of linear equations. 5. Lower triangular matrix. A square matrix where all the elements above the diagonal are 0. 5. For example, a 3 by 3 lower triangular matrix would be 7, 0, 0, 8, 9, 0, 10, 11, 12. 5. Lower triangular matrices are also used in linear algebra to solve systems of linear equations. 6. Row matrix. A matrix with one row and multiple columns. 6. For example, a row matrix with 3 elements would be 1, 2, 3. 6. Row matrices are used to represent vectors in linear algebra. 7. Column matrix. A matrix with one column and multiple rows. 7. For example, a column matrix with 3 elements would be 4, 5, 6. 7. Column matrices are also used to represent vectors in linear algebra. 8. Scalar matrix. A diagonal matrix where all the diagonal elements are the same. 8. For example, A 3 by 3 scalar matrix with the value 2 would be 2, 0, 0, 0, 2, 0, 0, 0, 2. 8. Scalar matrices are used to represent transformations that scale each coordinate by the same factor. 9. Singular matrix. A square matrix that does not have an inverse. 9. For example, a 2 by 2 singular matrix would be 1, 2, 2, 4, 9. Singular matrices can occur when solving systems of linear equations and have important applications in optimization and statistics. 10. Transpose of a matrix. A matrix where the rows and columns are swapped. 10. For example, the transpose of the matrix 1, 2, 3, 4, 5, 6 would be 1, 4, 2, 5, 3, 6. 10. The transpose of a matrix has important applications in linear algebra and geometry. Matrices have a wide range of applications in our daily lives. Here are some examples. 1. Computer graphics. Matrices are used to represent images in computer graphics. 1. They can be used to transform and manipulate images, apply filters, and create animations. 2. Business and finance. Matrices are used in financial modeling and portfolio optimization. 2. They can be used to represent the performance of different assets, analyze risk, and optimize investment strategies. 3. Engineering. Matrices are used in engineering applications such as structural analysis, control systems, and electrical circuit analysis. 3. They can be used to model and analyze complex systems, solve equations, and optimize performance. 4. Data analysis. Matrices are used in data analysis and machine learning. 4. They can be used to represent large datasets, perform statistical analysis, and build predictive models. 5. Cryptography. Matrices are used in cryptography to encode and decode messages. 5. They can be used to perform operations such as encryption, decryption, and key generation. 6. Robotics. Matrices are used in robotics to represent the position and orientation of objects in 3D space. 6. They can be used to control the movement of robots and simulate robot behavior. 7. Social networks. Matrices are used to analyze social networks and relationships. 7. They can be used to represent connections between individuals, identify patterns of behavior, and predict outcomes. 8. Game theory. Matrices are used in game theory to model strategic interactions between players. 8. They can be used to analyze the outcomes of different strategies and determine optimal choices. These are just a few examples of the many ways in which matrices are used in our daily lives. From computer graphics to finance to social networks, matrices play a fundamental role in many areas of modern life. Matrices have various applications in medical science. Here are some examples. 1. Medical imaging. Matrices are used to represent images obtained from medical imaging techniques such as MRI, CT scan, and ultrasound. 1. Matrices can be used to manipulate images, extract features, and enhance the quality of the image. 2. Gene expression analysis. Matrices are used in gene expression analysis to represent gene expression profiles of different tissues or cells. 2. Matrices can be used to identify differentially expressed genes, cluster similar genes, and visualize gene expression data. 3. Drug discovery. Matrices are used in drug discovery to analyze large datasets of chemical compounds and their properties. 3. Matrices can be used to identify patterns of activity, predict drug efficacy, and optimize drug design. 4. Epidemiology. Matrices are used in epidemiology to model the spread of infectious diseases. 4. Matrices can be used to represent the interactions between individuals, identify the most vulnerable populations, and predict the impact of interventions. 5. Medical diagnosis. Matrices can be used in medical diagnosis to analyze patient data and make accurate predictions about their health. 5. Matrices can be used to represent patient profiles, identify risk factors, and predict disease outcomes. 6. Bioinformatics. Matrices are used in bioinformatics to represent biological data such as DNA and protein sequences. 6. Matrices can be used to compare different sequences, identify similarities and differences, and predict the function of proteins. These are just a few examples of the many ways in which matrices are used in medical science. Matrices are a powerful tool for analyzing complex data, identifying patterns, and making predictions, and their use is likely to grow in the future as medical science becomes increasingly data-driven.